Okay, hello everybody. My name is Danny,
I'm Chris.
and we're doing Challenge 2, the optimal placement of waypoints.
So we're students at U of T. I'm in my third year of computer science, and Danny's in his third year of physics and math. And we're here to just kind of try out data science.
Okay, and that's enough about us. What was the task? The task stated in Challenge 2 was to determine the optimal placements of map boards for cultural centers in the city of Toronto. We were given a data set of about 1,300 cultural centers all over Toronto, and the challenge required us to determine the optimal locations to place the maps. But as we started talking with the City of Toronto mentors, we noticed that this had become, that the problem was becoming broader and broader. Eventually, the problem evolved into finding city hotspots. This was motivated by the wayfinding program, a City of Toronto app used to help tourists and residents unfamiliar with the City of Toronto find multimodal transportation and identify nearby solutions. So we began with a very narrow problem, which was to find optimal locations of map board placements. And it became a more sophisticated problem, which was to determine city hotspots. And as this problem becomes more sophisticated, we require more sophisticated solutions and more sophisticated data layers, which is something our solution reflects. So first we have just the cultural landmarks. As you see, they are indicated in orange here, and the green dots represent transit stops. In total, we worked with 3 data sets. The original cultural center data sets, which identifies all the orange dots here. The green dots, which represents the transit data, that is the transit stops all over the city of Toronto, as well as an additional data set that we mine from Foursquare, the social media app.
So the rationale behind getting data from Foursquare was that we wanted to essentially, after we were to place signs around the city, we want to essentially rank them by popularity. And one way of measuring that is to see how popular an area is. And we can do that using social media data, which offers some access to check-ins about venues. And Foursquare does that. So here we have the city of Toronto, and you'll notice these little blue dots on the screen. So these are essentially, in order to mine the data, I kind of divide the city into grids. And Foursquare had some API for extracting things based off latitude and longitude. But if you do a search in a grid, it only returns 50 results within an area. So eventually I just had to do a more finer grid search, which gave this data.
We divided our analysis into 2 parts. And this was imperative to our solution. Our 2 steps were clustering and ranking. So what we did first, we clustered the cultural centers locations, as you see here, by using the k-means clustering. So what this does, it identifies structure within the cultural landmarks data set. And this was important at this area because this is a largely unsupervised problem. We needed to obtain some structure as a baseline model. This shows what is known as the overlap penalty versus K. The overlap penalty is something that we came up with as a way to kind of judge how many clusters we should use. Of course, if we use 1,000 clusters, every single landmark gets its own cluster. But then it will become way too crowded. There will be way too much overlap, which you see on the right end there. More clusters leads to a higher overlap penalty. We were able to use this, and we were able to determine a reasonable K number of clusters to be used for K-means. For our example, which is about K equals 205. Of course, depending on how much money the city is willing to spend on this project and how closely they want the hotspots to be, K can be adjusted at your pleasure. Okay. This is the this is the map after we have applied the clustering algorithms. So in here we see that first we have the transit data in green, and we also have the cultural centers in their colored points, and the color represents which cluster they belong to. Of course, it's difficult to see all the clusters as there's a fair amount of points. So what we did is that for our baseline prediction, we predict the hotspots to be the centroids, or the arithmetic means of each of the clusters, which are indicated in red. Then, to evaluate how feasible this baseline prediction is, in here we also plotted a blue circle around each of the baseline prediction, the red X's. And this represents a 5-minute walk. So this is just a nice graphic to show you how k-means works. And here, we essentially divide the region of the city of Toronto into these many colored regions. The white marks represents the centers. So in here, we can see that the clustering works to some degree to identify structure in this data set. And the k-means was, the clustering was essential because the small data set, the cultural landmarks data set was relatively small. We were able to use k-means and iterate over k efficiently. We decided to use it at this spot on the cultural landmarks because if we had used it on larger data sets with the social media and the transit, it may have taken an unreasonable time to finish. Here we have a simple score. So in this case, we have what's known as scoring check-ins on Foursquare. We mine the Foursquare data, and for each X, that is the map board placement or the hotspot, we calculate how many check-ins are within some threshold radius. In this case, it was 500 meters, about a 5-minute walk. And you can see here that we use k equals 205, and that, non-surprisingly, we see some very, very high check-in scores near the downtown core. Similarly, what we also did was that we incorporated transit. How accessible is a hotspot to public transportation? This is done in a similar way. What we did is that we took the same radius and we instead calculated how many transit stops were in that radius. And as you can see here, it follows a similar pattern, not the exact same, but the majority of the highest scoring still rank in the city center. Now we're going to talk about our combined scoring. Our combined scoring in total consists of 3 parts: our check-in data, our transit score, as well as the size of the cluster. The size of the cluster is really important because obviously, if a hotspot is identified with a cluster that has a lot more points than another cluster, that hotspot is deemed to be more valuable or more important than one that does not have a lot of cultural landmarks nearby. Now we came to a part where we had to decide, how do we compare all this data, right? We're trying to come up with some final score, but how do we compare the number of check-ins to the number of transit stops? How many transit stops is 3,000 check-ins worth? And that's really a difficult question, and that makes tuning the weights of our final score rather difficult. What we did is that we instead normalized the scores to we computed the z-scores of all the scores of the size of the clusters, of the transit score and of the check-in score. And we use this to calculate our final score. This way, it is a little bit easier to see which scores we favor more. For our final score, just as an example, we put more weight on the number of cultural centers. In fact, we put twice the amount as we did on the check-in and the transit stops, mainly because we deemed the number of cultural centers to be a very important and robust indicator of hotspot activity. The weights can be adjusted to your pleasure. If you deem that you want accessibility as a primary concern, you will obviously increase the weight of the transit score. If you deem check-ins, if you are working with a lot of social media, you may increase the weight of the social media parameter. So this is largely based on comparative scoring, and this works because we already have a baseline prediction of k-means clustering, and now we just want some idea to rank the hotspots, which areas are hotter than others. And we do this by using our scores. Okay? And so these are our final scores that we have, top 5 scores. Of course, the ranking is not rigid. It's not this one is the best one. It's more of a loose ranking, as most unsupervised learning is. And here we see that the rankings are all in the downtown core, and that is a problem that there is a small problem with that, and that problem can be better explored if we go to the interactive map. So this is a similar plot, except this is an interactive map detailing the final scores of the City of Toronto of the hotspots. And as you can see here, green means very good. Red means still pretty hot, but blue means cold. There's not much activity going on. As you can see here, the majority of the hotspot activity is concentrated in the city center, which makes sense, while the suburbs is relatively cold. But of course, that raises a political problem that we just found out about today, and Chris will address that.
So after speaking to Fiona, we realized just how broad this problem is. So as you can see, most of these signs are clustered within the downtown area. But one thing that has to be considered is that many councils could benefit from this, and if there's wider support from them, they're more likely to go through. But the problem is they're so densely placed, and they're not necessarily appropriately weighted for these areas. For example, if you're in downtown Toronto, a 5-minute walk can get you anywhere very fast, and there's a lot you can see, but up north, for instance, you just can't get as far. You may not see anything, and that's how we've based our weighting right now. So there are 2 things we can do to address this to make this weighting and distribution of clusters a little more suitable towards the sparsity of the outer areas of town. One is simply to increase the radius we look over on the outer areas, and that will improve their scoring. And also we can have a kind of bias that as you get farther from the city center, there will be a kind of bias score which will increase the overall score of like clusters which are farther out, and so that'll benefit them. So these are just things to consider if we continue to develop this model.
Right. To add on what Chris says, it makes a lot of sense to set a dynamic threshold for the radius upon which around the hotspots around which we score them, because obviously a 5-minute walk in the city of Toronto is not the same as a 5-minute walk in Scarborough. So that is essential. That is a added feature that we can add if time allows. And in addition, so just wrapping up here, in addition, we can identifying hotspots in Toronto is not just useful for the city of Toronto, but it's also useful for businesses, especially businesses that use social media. because we have a social media aspect, this makes our model somewhat relevant to businesses, because businesses do not judge hotspots based on how many cultural centers are nearby. They instead judge it by some type of social media traffic. In fact, we can use the Foursquare data mining, to instead search for searches of, for example, if we were looking at a restaurant, we could search for, we could look at Foursquare check-ins that were searching for food, and this would be a fair indicator of which hotspots are more in demand for this business.
Just as a final aside, these business applications are completely independent of the city project. It's just these are ways that we can employ our model to solve other problems.
Okay, that concludes our presentation. Thank you very much. Are there any questions?
Questions?
Yes.
I'm just curious, how do you get the Foursquare data? Is that open source or?
So Foursquare offers an API they offer several APIs, a RESTful one, and do we have it open?
Yep, we have it open.
Okay.
It's right here.
Okay, so this isn't active right now, but they essentially expose methods which allow you to either get anonymized data. Where is it? Here it is. So here's just a simple REST request. You can specify a bounding box where you want to search over. You can specify categories, so we specifically focused on recreational areas and outdoor areas. And you simply pass it in, and then it searches. But as I said before, because it only returns 50 results per grid, per box that you search over, I had to I had to do a grid search with that. So there are some limitations. But you can also make 5,000 requests an hour, so it's very flexible in that sense.
Any other questions?
Yeah, so I'll maybe ask a question. Is this working?
I'll just
recorded it.
Okay.
And try to repeat the questions so that people back.
All right. So if the objective was to figure out where to locate these signage units, and you've looked at a 500-meter radius, or do I actually, I know that's the hot radius, but the signpost unit is actually just a square meter. Do I have a sense of where to locate that inside that 1 kilometer circle?
So we were just asked, so right now we're just placing your signs based off cultural landmark features, but it could be in the middle of a field, it could be in an apartment block. So we were asked, what is the best way, how do we ensure these are placed in a location which makes sense? One thing that we initially thought of was trying to find the closest major intersection, for instance. There are various ways to go about it, and traffic is another thing too. So we didn't decide that, but that is like
A next step.
a next step.
Okay, thank you very much.
Any more questions?
Is there a distinction of the type of signage that the program has for the city? Because I would imagine that even for intersection, pedestrian traffic volume is different from vehicle volume, right? So then chances are you targeting only pedestrian traffic, or we targeting, I have to have a sign that is big enough that the vehicle driver can see the direction.
Okay, so Augustine just asked who are the signs targeted towards and whether there are multiple versions of each signs. So these signs or the waypoints are being specifically developed for pedestrians. And they're meant to indicate things within a 5-minute or so walking radius, essentially. So no is the answer. It's just for pedestrians. Yes? You.
I'm just curious about which ones were the hotspots with the highest scores?
Places like the CN Tower. In fact, let's look.
So I'll do this. So as we can see here, there are some hotspots within the near Spadina and Adelaide around the city center. And if we expand the ranking to the top 10 or the top 20, eventually we'll see landmarks that are very familiar, such as the museum, the Royal Ontario Museum, the Bata Shoe Museum, places all over campus, and such places like these.
Yeah. And my other question is, how did you get the transportation score again? Is that only subway or is it bus stop?
So it's subways and bus stops. It's all kind of stops. I guess it could make sense to wait, to apply an additional weighting to stations since they have a higher volume of people. So that's something else we could have done. Yes, you had your hand up. Okay.
So first, I thought it was great that you guys had all the visuals because I thought that was really helpful to understand what your thinking was, and that really helped make it clear what was going on. The beginning of the presentation, you talked about the problem being an optimal placement. So there's sort of that implies some sort of optimality, some criteria that you're optimizing towards, and I didn't see a clear answer of where did you end up as far as how optimal your solution gets to be, and how do you feel that your answer fits into the original question that was asked?
So one thing that we kind of discussed was the subjectivity that we face in this problem. So these waypoints are meant to be catering towards multiple purposes, and that could be locating optimal or good footpaths, interesting landmarks, places for public transport. And because of this, and because of just the different way we've been measuring the data, it is essentially hard to find an exact optimal problem. And then ultimately, it's going to be left up to the experts to decide how to weight things.
Yes, you had a question?
Yeah, so if the city were to, base their sign placement based on this data, could you think of a way you could actually test, or some kind of control experiment to know that your method was optimal for sign placement?
So it can be a little difficult to measure this because let's say someone does go to a sign. I guess you want to figure out
How much does sign help them?
or, well, whether they go to a location or not, and then you would have to test again by replacing the signs or changing some aspects of them and see how it performs. So just off the top of my head, it seems very difficult to test.
We could do. A thought that just came to my head would be to see the social media response before the sign was placed, and then compare it to afterwards, and do a controlled experiment.
Thank you. I don't have any questions. Just delighted to hear your presentation. And in particular, the way in which you started to tackle the challenge, what we describe as the political challenges that we face when your thresholds start to change, whether in terms of walking distances and the political realities that we're dealing with. We did do, I'll mention when we were testing the maps, we did a lot of work on looking at where we've got the densification of these cultural assets, because it changes your scale, it changes everything. But we have not done that yet about the placement at that point in time. And it's one of the reasons that we've been thinking that these partnership opportunities might fill in a lot of the breadcrumb trails. But that's not a particularly scientifically pursued. So really happy about that. Thank you, actually. Just a quick caveat, actually. I realized that maybe I walk a bit faster because my 5 minute is 400 meters and yours is 500, but it's all good. So very happy to see that, but I'll just pass that along.
So is that snippet there on the website there, is that your final solution, like optimal solution?
No. So because k-means is a non-convex problem, we didn't search over all the possible initial configurations of points. So that'd be one way to improve it. You probably noticed a different distribution from this morning. Yeah, so that's it.
And just as a quick, if that is like I guess an optimal solution, is there anything that by eyeball or weirdness that kind of sticks out to you as to why that would need to be revisited? Is there any anomaly or something that's unintuitive about that? And the answer should be yes. But beyond that, what is the kind of very unintuitive result if that is the optimal answer, the optimal placement? Is there any sanity check that?
So I'll just repeat the question. The question was that, is there any part any intuitive parts to this model that we can identify and then fix? Yes, this model has some limitations. And one point that you can see that these points are all closely located. In fact, they can all be sort of on one street, if you want. And this is a limitation to our model due to k-means clustering.
Yeah, so what I was thinking of is like, why not Union Station? Why isn't Union Station like lit up in like green? But like the green spot there is at University in Adelaide, which kind of makes sense there too. But so like when I first saw that, I whispered over to my counterpart here. I was like, why not Union Station? I don't know.
So we were mainly factoring in. In fact, we're only factoring where people were going to as endpoints. We weren't considering where people may have been passing through in volume. So that is one limitation to what we've done.
Oh, that's fine, yeah. And just I don't know, we'll see how this question goes. Imagine I'm John Tory.
Okay.
How would you explain k-means to me?
I wouldn't. Instead, I think the best way to go about this is that we have, in fact, here.
I would say it's a revolutionary, top-of-the-shelf clustering algorithm designed to give accurate structural clusters of the city of Toronto. That's something I would say. And
or maybe a more intuitive way would be just to explain that we are basing signs. We're basing signs where locations or areas of interest are dense or densely collected, and that our model favors that placement.
And also to address your Union Station problem, the Union Station problem, I believe, is a result of the fact that we identify the billboards to be this arithmetic means. As you can see here, even if Union Station has a lot of cultural landmarks, on this side, there's nothing. It's just the lake. While on this side, it's populated by more points. So this may effectively drag the center up. And this is a limitation of our problem, especially when we have non-symmetric clusters such as that.
Any more questions?
But wouldn't you sort of treat your algorithm in such a way that maybe in transit or major sort of exchange between different transit systems, where you have the highest pedestrian flow that are taking subway down to Union Station and come out and go to UJ Game. And chances are those locations will have a higher value to you than just a simple KB, because that, within your cluster, then you have the transit mixer, then maybe you should place it right there, because then a lot more people will pass it.
So just to clarify, you're just talking about basing our clustering more on pedestrian volume, right?
No, I'm not saying one or the other. I'm saying both. It's a genius of both.
Right.
So when you have a cluster that has a transit station there, but then your central is over here, then it makes sense to put the signage closer to the exit.
Right, and as we mentioned, we would eventually try to place signs somewhere which is more. So, for instance, if our center of a cluster is in the middle of an apartment building, it would make sense to place it initially just like next to a major intersection. And of course, it would make more sense to factor in volume, but that's another way we could modify the model.
And just to add on that, one thing that we can do is that going back to an earlier slide, this one where we divide the city up into clusters, instead of using the centers or the arithmetic means, once we divide the city into these partitions, then we can optimize over where in the cluster we wanted to put the sign. The centroid is just a very naive and rough estimate. And the reason we didn't focus more on that is that we received additional information about the context of the problem, which was instead identifying hotspots and which spots were more hotter than others. So we decided to go for a more comparative ranking rather than deciding the optimal location for the map board. We decided to rank which hotspots were better than others. Any further questions? Yes.
I guess I'm curious to know, just pique your thoughts. Other than sign placement, what do you envision for this data can be used for as well?
Yeah, we touched briefly on business potential. So essentially what we're doing is we're doing a very broad analysis. We're analyzing hotspots in the city of Toronto, where people are likely to go, where people are likely to be, where people are likely to have fun. Our main distinguishing features are that we use clustering, and then we use ranking, and this gives us a baseline prediction for that. But there are many other applications, such as businesses who want to identify perhaps where to open up a new store. They can identify which spots of the city are hotter for them than others. Of course, it'll differ for a restaurant than it will for an IKEA. So using our similar methods and adjusting the weights appropriately and filtering the social media searches, we can see that there are numerous business applications for our model.
We should probably be closing out. It's been over half an hour, so is there a last question at all? Thank you.